Swayam Prabha. Digital India. Educated India.
Hello and welcome to this concluding lecture on Routh array. Okay. So, we have been discussing about this Routh array over the last 3 lectures or so. So, in this lecture we will take up some examples, and at the same time we will now also finalize and finally tell you that all may not always be well with the sort of polynomials that we will be dealing with, because if you recall in the last lecture we have apparently given you some sort of a sketch or a rough idea of why the Routh array not only allows you to tell if all the roots are on the open left half plane, but also in case they are not, it also tells you how they are distributed on the open left half plane and the right half plane. One thing we have very cautiously always avoided is the possibility that the root is exactly on the imaginary axis, okay. But in real cases you might always encounter such situations where the roots of the polynomial are purely imaginary, okay. So, that is one singular case, okay. So, we will see what happens when we encounter such situations. There is also another kind of numerical sort of a problem that you might run into, okay. So, without sort of belaboring that point again, let me just take a quick example and show you what sort of a problem you might potentially encounter. So, again as usual, instead of taking the usual Routh array, I will just take the polynomial and try to show you what this is. So, let us take the polynomial s to the 5 plus 2s to the 4 plus 3s cubed plus 6s squared plus 5s plus 3, okay. So, we split this up into s to the 5 plus 3s cubed plus 5s, as usual an odd part and an even part, which is 2s to the 4 plus 6s squared plus 3, okay. And then in the next step, when we want to reduce this by 1 degree, we keep the even part intact here because the odd part contains the highest degree term, plus now we have s to the 5 plus 3s cubed plus 5s minus, we will need to multiply this by half s, yeah, 2s to the 4 plus 6s squared plus 3, okay. Yeah, now what are we left with? 2s to the 4 plus 6s squared plus 3 plus, notice that the s to the 5 goes off, but here is something interesting that happens. In your bid to get rid of s to the 5, you have multiplied it by a suitably scaled factor here, and what you have ended up in the process is also eliminating s cubed. Notice that the coefficient of s cubed is 3, and if you multiply in this fashion, yeah, in the remainder the coefficient of s cubed is also 3. So, 3 and 3 cancel out, 3 and minus 3. So, what you will then be just left with from this part is 5 minus 3 by 2 s, yeah, and that is equal to 2s to the 4 plus 6s squared plus 5 2s are 10 minus 3, that is 7, 7 by 2s plus 3. Now, in so far as deducing about the roots of this polynomial, the moment you have some coefficient missing, okay, you can always treat it in the same manner as you would treat a change of sign, yeah. So if you have a coefficient missing here, excuse me, you can immediately deduce that this polynomial P1s cannot have all its roots on the open left half plane, and therefore it does not satisfy the interlacing property, and if it does not satisfy the interlacing property, neither does PS, and if PS does not satisfy the interlacing property, PS also does not have all its roots on the open left half plane, hence you have the answer. So for the purpose of answering that question which we started with in 3 lectures back, that is well and truly answered at this point. But recall in the last lecture or in the preceding one before, we saw something else. We saw that the Routh array not just tells you if all the roots are on the open left half plane, but it also tells you the distribution. But in this case, clearly you are now stuck. Why? Because remember, your Routh array always requires that you should be able to, now in the next stage when you look for P2s, you want to get rid of this term. How? You want to get rid of this term by multiplying the odd part of this polynomial with s times some suitable scaling factor. But to your horror, you now see that the odd part does not have an s cubed term, it only has this s term. Yeah? So what can you do then, right? What is it that you would possibly do? Yeah? So the idea is as follows. The idea is, it comes from the idea of, I am not going to again prove this, the so called continuity of roots. What that says is, if you take a polynomial, now for quadratic, for example, for a quadratic polynomial, you know that the roots of a quadratic polynomial are minus b plus minus square root of b square minus 4ac by twice a, where a is obviously not equal to 0. If a were equal to 0, then it wouldn't be a quadratic polynomial. So for you discount the fact that a is equal to 0, and then what you arrive at is that if you see how the roots vary with b and c and even a, you will see that the roots vary continuously as the coefficients of the quadratic polynomial. The same thing holds true for any polynomial. Even though we do not know exactly what the function is in a closed form, like how every single coefficient is affecting the root, yeah, we do not know that in closed form. For example, in quadratic, you know that if you increase b, this happens to the root. If you increase c or if you decrease a, this and this happens to the root. The root changes in this fashion. In this polynomial, in this of 5th degree, I do not really know what happens if I change this 2 to 2.1 or if I change this 5 to 5.5. I have no way of telling directly because I do not have an explicit formula for the roots of this polynomial in terms of its coefficients. As I said, beyond 4th degree, such formulae do not exist, right? But what we still can say is that if you make very small changes in these coefficients, so in other words, if you have Ps and if you have P epsilon s, where Ps is given by a0 plus a1s plus dot 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 till an s to the n, and P epsilon s is nothing but a0 plus epsilon 0 plus a1 plus epsilon 1 s plus dot 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 till an plus epsilon n s to the n, okay. And if for all epsilon I less than some epsilon, yeah, it turns out that if you draw on the complex plane, if you draw small circles around the roots of the original polynomial, which is, let us say, the roots of Ps, okay, if you draw really small enough circles around them, okay, where this epsilon can be determined. This is just a continuity argument. You can look this up, it's there, it's a standard result. The point is, if this small circle, right, if this small circle contains a root of multiplicity, let us say ti, if this is pi with multiplicity ti, that means there are ti repetitions, so copies of pi as roots, okay, then this polynomial p epsilon will also contain exactly ti roots, not exactly repeated, but within this small circle, very small circle around the roots of the original polynomial, you will find exactly ti roots of the perturbed polynomial. Okay. So this is a continuity argument that I am making. Why is this continuity argument important? Because now that I have encountered a situation where this s cubed coefficient has vanished in P1s, I am going to just consider P1 epsilon s, and I am going to call it 2s to the 4, 2s to the 4 plus some epsilon times s cubed plus 6s squared plus 7 by 2s, 6s squared plus 7 by 2s plus, what was the last term, 3, plus 3, okay. And I am going to claim that because the coefficients of P1 and P1 epsilon are very close by, after all this epsilon is only a small quantity, no, just like I claimed here. So therefore, the actual roots of P1 and the roots of P1 epsilon, so the argument is that roots of P1 and P1 epsilon are very close, okay. So there is only one situation where you might run into trouble here. Suppose all the roots of P1 are either in the open left half or in the open right half, like so. So then you see that the roots of P1 epsilon, so let us say the black ones are roots of P1, and let us say the blue ones I am trying to, going to draw circles around them. So these are very small circles, epsilon size circles, okay. It is a continuity argument as we generally do, okay. So what I am then saying is that the roots of P1 epsilon, although I do not know where they are exactly, but I know that they will be in and around some small neighborhood of these roots of P1, okay. So therefore, the overall distribution, which is what the Routh array tells me, insofar as the distribution is concerned, the distribution of roots of P1s, or in other words the signature of P1 is equal to the signature of P1 epsilon, yeah. Of course the degree is the same because that is how I have cooked it up, no. Now degree of P1 is equal to degree of P1 epsilon, this is by choice, and this is by continuity argument, okay. I know it might not appear very foolproof or very concrete, but trust me that this is true, that indeed if you perturb the coefficients only ever so slightly, the roots do not go very far from the original roots, okay. So they are constrained to lie within a very small neighborhood around this, okay. Of course, provided that you do not change the degree of the polynomial itself, right, then you are actually losing one root in its entirety. So now, if as we have seen that the degree and the signature uniquely specify the distribution of the root, that number L and R, the number on the LHP and the number on the RHP. So therefore, now if I want to carry on with the Routh array, at this point I saw that I am stuck with the Routh array, no, because I do not have an s cubed. But now if I want to carry on with this Routh array, yeah, what I can then do is I can hereafter, instead of studying P1, I can study this P1 epsilon. So at the next stage what I am going to do is, I am going to say that P2 I can obtain as, of course I am going to retain this epsilon s cubed plus 7 by 2s, the odd part I am going to retain, and the even part I am going to just say it is 2s to the 4 plus 6s squared plus 3, and now because I have a non-zero term to play around with, albeit a very small number, but I can still take this 2 by epsilon times epsilon s cubed plus 7 by 2s, okay, and I will get hereafter epsilon s cubed plus 7 by 2s plus this 2s to the power 4 now gets cancelled because of this, okay, there is the s I am missing. So this 2s to the power 4 gets cancelled here, and what you are left with is 6s squared, so it is 6 minus, this is 7 by epsilon, yeah. So, this 7 by epsilon s squared plus 3. So, clearly you see that for very small epsilon this is going to have a change of sign, yeah, as we just deduced also. No, we also deduced that there is immediately the moment you encounter this sort of a situation, the question about whether all the roots can lie on the open left half plane, that is already gone. It cannot. The moment you encounter such a singularity, you cannot have a polynomial all whose roots are on the LHP. That possibility is nipped in the bud. But why did we still carry on with this Routh array? Why were we insistent on carrying on with this epsilon approximation? The reason being that we want to also talk about the distribution. So, we want to look at the number of sign swaps. So, hereafter, now that you have seen this, I am going to now cook up the Routh table for this with this epsilon modification, and we will show you what this modification entails. Okay. So, let us say, let me start with that s to the 5 plus 9s cubed plus 35s squared plus 50. Is that the original polynomial? Oh, sorry, I am sorry. I am actually going off on a different polynomial altogether. I have not chosen, it's the original s to the power 4. Yeah, sorry about that. I was probably talking about the next example that we are going to take. Yeah, I was jumping the gun. So, s to the 5 plus 9s cube, 2s to the 4 plus 2s to the 4 plus 3s cubed plus 6s squared plus 5s plus 3. Okay. So, there are a few ways, not just this epsilon method that I have spoken about, there are a number of ways of bypassing this difficulty and still continuing with the Routh array and finally concluding from the number of sign swaps in the first column as to the distribution of the roots. Okay. So, let me just quickly write that down here, this will be more efficient, I hope. So, here you have 2, 6 and 3. Okay. So, now we go about this. So, 2 3s are 6 minus 6. So, immediately you see that you encounter this 0, yeah, and then you have 2 5s are 10 minus 3 7. So, that is 7 by 2 and 0. So, now instead of this 0 we cancel this off and we replace this by an epsilon, that is what we did, right. So, when we go to the next row we just multiply this by epsilon. So, this is 6 epsilon. So, 6 epsilon minus 7 upon epsilon, right. What about this? This is 3 epsilon minus 0 upon epsilon. So, this is 3. Then you go to the next row where you have this, okay, this is a nasty calculation. You will have 7 by 2 minus, I believe it should be 3 epsilon over 3 epsilon squared upon 6 epsilon minus 7. Okay. Yeah, and the rest is 0, and finally here you will have 3. So, now the question is, how do you study the sign change here? So, either the trick is either take epsilon greater than 0. So, in that case this is positive, this is positive, this is positive. What about this? Here you have 6 minus 7 by epsilon, no. So, 6 minus 7 by epsilon, what is it? Epsilon is very small. So, 7 by epsilon is much larger than 6 in magnitude, yeah. So, therefore, this is negative. So, there is a sign swap here. Now, you go to the next step. What is this? This is 7 by 2. What is this? Notice that as epsilon tends to 0, the denominator degree is less than the numerator degree. So, this goes to 0, right. So, this is 7 by 2. So, this is again positive and this is positive. So, if you look at the first row, first column here, there are 2 sign swaps. There are 2 sign swaps. Therefore, the distribution is L is equal to 3, R is equal to 2. Okay? And of course, L plus R is equal to 5, right? And the signature is L minus R is equal to 1. So, that is the deduction. Simple. But you may not be very happy with this epsilon method. Of course, this epsilon method generally works, but you know, someone might say, okay, I am not very happy with this, this does not sound very mathematically sound. So what then can you do? There is one way to get around this problem which sometimes works but not always. So even if you had taken, for instance, epsilon to be negative here, you see the count of the sign swaps would not have changed. For example, if you had taken epsilon to be negative at this junction, then the first sign swap would have occurred here, right? And then at the next instant when you do here, what would have happened if epsilon would have been negative? Then this is basically what, 6 minus, so this will be some 6 plus, sorry, this would be some negative epsilon, no? So then once the negativity has come in here, so there would again be at this junction, again here, you will come across the conclusion that this next sign swap would have been here. So any case you would have had two sign swaps, one sign swap from positive to negative here, and then one from negative to positive, I guess here, right, or maybe in the previous step itself, yeah, no, that would not have changed. So what I am trying to highlight here is that whether you take epsilon positive or negative, it would not matter, yeah, so long as you take epsilon to be a small number magnitude wise, you will still have the same number of sign swaps. I guess, yeah, the variable does not change. So if you take epsilon to be slightly negative, then the second sign swap would have occurred here. So you would still have had two sign swaps even with a negative value of epsilon, yeah, it would not matter. Notice that if you have a polynomial, say for instance s minus z1 into s minus z2 dot 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 till s minus zn, okay, let us say these are not necessarily all distinct roots, okay. So this is the polynomial. Then you consider the p bar whose roots are s minus 1 by z1, s minus 1 by z2, so on till s minus 1 by zn, okay. Notice that if zi belongs to open left half plane, 1 by zi also belongs to open left half plane, and similarly zi belongs to open right half plane, 1 by zi belongs to open right half plane, and zi belongs to imaginary axis, then 1 by zi also belongs to imaginary axis, okay. So insofar as the root distribution of p and p bar are concerned, yeah, so degree of p is equal to degree of p bar, and signature of p is equal to also signature of p bar, yeah. So therefore we will see that the distribution of the roots are one and the same for these two, okay. Now what is so special about this p bar? If you give it a moment's thought, alright, you will see that the coefficients of p and p bar are just the reverse of one another, okay. So it is just a reverse polynomial. How so? How so? In the following manner. So you pick out s to the n from here, okay, and then you have 1 minus 1 by s z1 dot 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 till 1 minus 1 by s zn, yeah. So p bar is equal to 0 implies that, you know, this polynomial is, of course we know what the roots are, right. So in what way can we write this polynomial down, right. So let 1 by s is equal to some other variable, what can I call it, let us say w, yeah. So now if you look for the polynomial in w, yeah, you will see that it is exactly the same as this p, okay. So that is why this reverse polynomial has its coefficients in reverse order. Let me take this particular example. You see, after all, this fact that we encountered this 0 here is because of some numerical factor. No, it just so happened that when we were cancelling out this 5th degree, we also cancelled out this 3rd degree coefficient. So there is a chance that we can at least hope that if we consider this reverse polynomial, maybe, because after all studying the polynomial is the same as studying the root distribution of the reverse polynomial, the root distributions are the same. So maybe we can bypass this problem of encountering this epsilon if we took the reverse polynomial. So let us try that. So if p is equal to s to the 5 plus 2s to the 4 plus 3s cubed plus 6s squared plus 5s plus 3, then p bar by our nomenclature would be 3s to the 5 plus 5s to the 4 plus 6s cubed plus 3s squared plus 2s plus 1. So let us try to cook up the Routh array for this. So for p bar, let's say we take s to the 5, s to the 4, s to the 3, s squared, s to the 1, s to the 0. So we have 3, 6, 2, 5, 3, 1. So 5, 6 are 30, minus 9 is 21, so it's 21 by 5, okay, 30 minus 9, 21 by 5, 5 2s are 10, minus 3 is 7, so it's 7 by 5, okay. Now in order to obviously simplify this, we don't want to have these fractions and all, so we can scale up, as I said earlier also in an earlier lecture, that we can scale up or down these rows. So let me get rid of this 5 here, let me just have 21 and 7, and then further, why not also reduce this? So I can reduce this to 3 and this to 1, yeah. So this is just a ratio of 3:1. So dividing throughout by 7 by 5, I can get 3:1. So when I go to the next row, what do I have? 3 3s are 9, minus 5, that's 4. So that's 4 by 3, and 3 1s are 3, minus 0, that's 3 by 3, that's 1. So once again I can sort of simplify this and make this 4 and make this 3. Now what do I encounter at this S1th row? 4 1s are 4, minus 3, that's minus 5 by 4, okay, and a 0 here, right. And finally, when I come to this final row here, I see that it's 5 by 4 into 3 minus 4 into 0, which is basically going to be 3 by minus 5 by 4, yeah. So this is 3. So now look at this reverse polynomials number of sign swaps. Again positive, positive, no swap, no swap, no swap, one swap and another swap. So there are 2 swaps. Exactly what we deduced from an analysis of all of this epsilon and this stuff that we did here. Only thing that we had to take all these limits, epsilon tending to 0 and all of this funny things we had to do with epsilon, no, in order to deduce, because looking at these expressions from the first row, first column here, nothing stands out as positive and negative numbers like it does here. So that's why this reverse polynomial technique often works, but then sometimes it doesn't work, and I leave you with one such exercise where you can try and see that this reverse polynomial will not work. So whether you try out this Routh array with the original polynomial or with the reverse polynomial, in both cases you will encounter this singularity, this 0 at some stage, okay. So try out with this polynomial, this is an exercise for you, this will also give you some practice. So try both p and p bar, where p bar is a reverse polynomial, and you will see that in both cases you cannot bypass this difficulty of epsilon, this 0 appearing in the first column here, okay. Now there is also another method which some people often use. So here if you have been given an nth degree polynomial, you multiply it by some s plus a, where a is some large positive number. So then you already, instead of studying ps, you study s plus a times ps. So if ps is of degree n, this will be of degree n plus 1, yeah, and then you carry on with the Routh array. Sometimes this helps. So try out this technique as well with this polynomial instead of, so there are 3 ways we have seen. One is the epsilon method, one is the reverse polynomial method, the third is, of course I am not showing you an example of the third one, but you choose this to be some large number, let's say 50 or 100 or 10, whatever, yeah, and it turns out that if you choose such numbers, you can often bypass this difficulty of encountering a 0 in the first column, okay. So try this out with this particular problem and figure it out for yourself. You will still see that you will come to the same conclusion, that this polynomial has the same number of roots as its reverse polynomial and as does its so called augmented polynomial. So this I am calling the augmented polynomial. So I know already where this extra root is being added, so the original root distribution remains intact, only the number of roots on the LHP gets increased by 1. If I just take that into account, I can just carry on with this augmented polynomial, let us call this P tilde. So that is a third method. So we have shown you 3 methods of overcoming this particular glitch in the algorithm. Turns out there is another way in which you can encounter a glitch in the system. How so? Okay. So let me start with another example here. That is probably the best way to show you how this works. 7s to the 4 plus 6s cubed plus 42s squared plus 8s plus 56. Okay. So let me quickly cook up the Routh table here, since by now we have sort of grown used to this Routh array. So first row will be 1, 6, 8, second row will be 7, 42, 56. What about the third row? Third row would be, okay, what about the third row? 7, 6 are 42 minus 42. So here you encounter this where you have a 0 here, and on the face of it, it seems like this is the same as the earlier problem, no? But notice carefully, this is actually not the same as the earlier case, because here instead of having the 0 only at the first column, you have the entire row of zeros. So this is a second type of singularity. Do not make the mistake of thinking that this is exactly the same as the first type of singularity, where you have only, notice here, where you encountered this singularity here, there was only a 0 in the first column, but the second column did not have a 0. So you did not have an entire row of zeros, but here you now encounter 7 8s are 56 minus 56, so this entire row is 0. So this calls for some drastic measures, some other way of possibly tackling this, and also of interpreting what this basically means. So in order to interpret what this means, let us go back to our original algorithm. So we have Ps is equal to s to the 5 plus 7s to the 4 plus 6s cubed plus 42s squared plus 8s plus 56. Okay. So now let me try and get P1s from this. So I am going to first keep the even part intact, plus 42s square plus 56s plus, now I am going to try and subtract this s to the 5 plus 6s cube plus 8s minus, what do I need to do? I have to adjust by s by 7. Yeah, if I adjust by s by 7, then I have 7s to the 4 plus 42s squared plus 56s. But lo and behold, what have I done? At the end of this step, I encountered this curious scenario, where not only is the first term gone, which was as desired, not only is the second term gone, which I have thus far encountered in my previous singularity, but all the terms have gone. So in my bid to nullify this s to the 5, I have eventually made all of this 0. What does this mean? This means, notice very carefully what I am going to say now next. This means that this original polynomial, yeah, this original polynomial can be factorized. Okay. So what I have obtained at the end of this first iteration here, this polynomial is basically a factor of this original polynomial. Why? Think carefully about the operation we are doing here. We have this P odd plus P even. This is our P. And now at the next stage, when we do this P1, what are we actually doing? We are actually keeping the P even intact, and then we are saying we are going to do this P odd minus some s times an upon an minus 1 P even, right. Now if this turns out to be 0, then what does it mean? It means that this p even is a factor of p odd, because p even, this is, remember, the divisor, this is the quotient, and this is the dividend in the long division, isn't it? So this is the dividend, this is the quotient, this is the divisor. In a sense, what this Routh array was spitting out thus far was the remainder. But now, if this term is 0, this term within the third bracket is 0, it means that the remainder is 0. What does it mean to say that a remainder is 0? It means that the divisor divides the dividend perfectly, that the divisor is a factor of the dividend. So if the divisor is a factor of the dividend, it means that p even is a factor of p odd. Of course, p even is also a factor of p even itself, just multiply p even by 1. So therefore, p even is a factor of p even is a factor of p odd, therefore p even is a factor of p. But what does that tell me? What do I know about p even? P even, so in general this could also be p odd is, if you encountered this with, let's say, a 6th degree polynomial, excuse me, yeah, you could have also encountered this, yeah, in a reverse order, right? So you keep the p odd intact here, and then you find out that this is a factor, okay? So in general here, we'll just talk about this particular case here, but it could be the other way around as well, okay? So what happens, what this means is that this p even is a factor of p. So if p even is a factor of p, then it means that from this stage onwards, in going from p1 onwards, I need to study the root distribution of p1, which is p even. But what is p even after all? P even is an even polynomial. What do I mean by that even polynomial business? What I mean is that p even contains terms of the form s to the 2k only for k belonging to the set of positive integers, or rather positive integers and 0. So basically, p even is an even polynomial. It means that p even, notice any example here, for example here also you see, what is p even? It contains s to the 4, s to the 2, that is why it is called an even polynomial. What is a feature of an even polynomial, or for that matter an even function? So if you take p even of s, it is equal to p even of minus s. So then what can I infer about roots of p even? Roots of p even, this then means roots of p even are symmetrically distributed about the origin. Why? Because if s is a root, remember, why is this so? If p of s, p even of s is equal to 0 is true for s is equal to s1, it is also true for s is equal to minus s. Why? Because ps is equal to p minus s, so ps1 is equal to p minus s1. No? So if s1 is a root, then minus s1 is also a root. Now in the context of this complex plane, what does it mean? Suppose this is s1, then what is minus s1? Minus s1 is going to be just the reflection about the origin. So this is minus s1. But what do we also know? If s1 is a root and it is complex, then s1 conjugate is also a root, no? And by the same token, you can also say that minus S1 conjugate is also a root. So what are the different ways in which the roots of this polynomial can be distributed? Either they can have roots distributed like this, where specifying one complex root specifies 4 complex roots, or they can have roots that are real, in which case this is S1, this is minus S1, or they can have purely imaginary roots, something that we have discounted thus far, something that we haven't spoken of so far. So this is minus S1 and this is S1. So these are the situations which can occur. And if something is a root of P even, is it also not a root of P? Because after all, P even is a factor of P. So then the moment you encounter a situation like this, a singularity like this, like you encountered here, a row of all zeros, a row completely comprising zeros, you are sure that you have an even polynomial which is a factor of this original polynomial, and in fact it is basically nothing but the polynomial in the preceding row. Okay, and also you know that the roots of that particular polynomial are distributed in this fashion. But that is not enough. See, how do you know whether it's this scenario that is occurring, or it's this scenario that is occurring, or it's this scenario that is occurring? What if it's a mix of all of them? So what if you have a combination, you have something like this, yeah, you have all of this. So suppose it's like an 8th degree polynomial, this P even is an 8th degree polynomial, and it's, let's say, coming from a 12th degree original polynomial PS, which upon reducing at some stage you encountered this row of all zeros, and the preceding row is corresponding to s to the 8. Okay. Now this could well be a distribution. Also, this could well be a distribution, no? So how do you know which one is it? Just the fact that you have all zeros in the entry for s to the 8, how do you know whether it's this scenario or this scenario? Yeah. So in order to bypass this problem or address this problem, here's the observation, and once again I'll give you a hint as to why this works. This is based on Rolle's theorem. So Rolle's theorem says that if you have a function fx which is continuous in the closed interval ab, so it's continuous in the closed interval ab, it's differentiable in the open interval ab, yeah, continuous in the closed interval ab, differentiable in the open interval ab, and if f of a is equal to f of b, okay, so this is one condition, this is two condition, this is the third condition, then there exists C in the interval AB, C in the interval AB such that f dashed C is equal to 0. Okay. How does that help? Well, you see, if the distribution of the roots are in this fashion, okay, if the distribution of the roots are in this fashion, all the roots, all the 8 roots are on the imaginary axis, then what do? Let's say you have P even S plus DDS of P even S. What does Rolle's theorem tell me about this? You see, this is the interesting bit. Now you take P even omega plus j times dd s of p even s at s is equal to j omega. Okay. Let me forget about this j here. So this is dd, we differentiate with respect to s, okay, we differentiate with respect to s, p even s, and let s is equal to j omega. So if you differentiate this with respect to s, this will eventually turn out to be some odd polynomial, because we don't have an odd polynomial. You see, in order to continue with the Routh array, we need something here, otherwise the next step we cannot proceed. So we cook up something like this, and what is so special about this particular way of cooking this up? Rolle's theorem tells me that if you have 2 zeros of p even, yeah, so if you have, for example, omega I and omega I plus 1 as two zeros of P even. What does it mean? It means that P even vanishes on the imaginary axis. Yeah. So between two such zeros of P even, you see the derivative of P even must vanish because of Rolle's theorem, because it is a continuous function, it is differentiable in this interval, therefore it must vanish, the derivative must vanish, and therefore the interlacing property will hold true. So listen to this bit very carefully. This is the crux of the matter. The crux of the matter is thus: once you encounter a situation such as this, yeah, now you no longer are interested in the original polynomial, now you will be studying this reduced polynomial. Yeah, so you will be studying this reduced polynomial, but this reduced polynomial we know has roots in a symmetric distribution. On the other hand, this reduced polynomial has no odd part. How do we construct the odd part? If we construct the odd part in this fashion, then we know, and this is the observation, note very carefully, we know that if the even part has only, so let me make that claim, if P even S has all its roots on the imaginary axis, it means that P even plus DDS of P even has all its roots on OLHP. That is it. Why? Because you see, the fact that the way I have cooked this up, if this has all its roots on the imaginary axis, then by virtue of this Rolle's theorem, the interlacing will be true, because then the way I have cooked up this odd part is bound to have one root between every two successive roots of the even part. So therefore, I have constructed for every even polynomial which has purely imaginary roots only, I have actually constructed a new polynomial which will always have all its roots on the open left half plane. Okay. So therefore, if I now replace this, if I continue this table here, where is that table? Have I actually drawn the table? I haven't drawn the table. Okay, I will draw the table, that will make it clearer. Okay. So if I now draw this table here, what I will then be studying is, if I am studying the nature of the roots, if I am trying to ascertain whether all the roots of this new polynomial that I have cooked up are on the open left half plane, it is the same as studying if all the roots of the even polynomial are on the imaginary axis. Okay. So the number of sign changes will tell me that those many are not on the imaginary axis. How so? Let's finish this example. Let's finish this example and then I'll give you one more exercise to try out. So here, s to the power 5, okay, let me cook this up here. Go to the new slide. S to the power 5 plus, okay, what was the original polynomial? Sorry about that. 7s, okay. Yeah, s to the 5 plus 7s to the 4 plus 6s cubed plus 42s squared plus 8s plus 56. So if you want to cook this up now, s to the 4, s cubed, s squared, s to the 1, s to the 0. So this is 1, 6, 8, 7, 42, 56. And then we encountered this row of zeros where we thought the case was hopeless. But now what we are going to do is we are going to differentiate this. So 7s to the power 4 plus 42s squared plus 56. So we are going to take the differentiation of this and use that to fill up this row of zeros. Okay. So we are going to cut this out. Okay. So this is 28s cubed plus 84s. Okay. So we are going to take this, replace this with 28 s cubed plus 84s. Okay. So we can again scale this down. We don't want to deal with such clumsy numbers, no. So this is yeah, I think this is 3, no, 22s are 56, yeah. So this is 1 and 3. So then we go to the next stage where we have 42 minus 21 by 1. So that's 21. Then 1 into 56 minus 0. So this is 56. So again at this level we can reduce this. 7 3s are 21 and 7 8s are 56. So now we get 3 3s are 9 minus 8, that's 1 over 3. So 1/3. Yeah, 1/3, and 3 zeros are 0 minus 0, so that's 0. And finally we have this 8. So you now look at this. So look at this first column. You see there are no sign changes. It means that this stage onwards, when I have been looking at this new polynomial 7s to the 4 plus 28s cubed plus 42s squared plus 84s plus 56, this polynomial onwards everything is Hurwitz. And if this is everything is Hurwitz from this onwards, then these roots are interleaving. Yeah, and if these roots are interleaving, yeah, then I know that the roots of this polynomial are all imaginary. So therefore 7s to the 4 plus 42s squared plus 56 has 4 purely imaginary roots. Okay. So what about the other root? Of course these 4 are also roots of the original polynomial. So the original polynomial also has 4 imaginary roots, purely imaginary roots. So there is one more root remaining. What can we deduce? For that we need to deduce from the number of sign swaps up to this point. So the trick is, the moment you encounter the 0, everything that precedes that row of zeros is talking about the factor. Okay. And everything that follows this row of zeros thereafter is talking about this polynomial. It's precisely, it's telling you that if there are no sign changes, then all the roots are on the imaginary axis. If there are, let's say, 2 sign changes, then there are 2 roots on the right half plane, and consequently because of the symmetry there will be 2 roots on the left half plane. So for example, if there were 2 sign changes here, from this row onwards, if there were 2 sign changes, then I would have deduced that all the 4 roots are distributed in this fashion, 2 on the left half plane, 2 on the right half plane, okay, and none on the imaginary axis, and therefore the original polynomial would also have 2 on the left half plane and 2 on the right half plane from this point onwards, and 1 on the left half plane originally. So the root distribution would have been 3 and 2, 3 on the left half plane, 2 on the right half plane. Instead of going about it this way, let me take another example. Okay, so let's take this final example. S to the 11 plus s to the 10 plus 12s to the 9 plus 22s to the 8 plus 39s to the 7 plus 59s to the 6 plus 48s to the 5 plus 38s to the 4 plus 20s cubed. Now obviously this looks like an 11th degree polynomial, but essentially you see you can pull out this. You already know that you can pull out this s cubed, and then this becomes an 8th degree polynomial. Yeah. So let's do that at the very first stage itself before applying this Routh table. So this is yeah. So this is S7 plus 12S6 plus 22S5 plus 39S4 plus 59S3 plus 48S squared plus 38S plus 20. Okay. So I already know that there are 3 roots at the origin. Forget about it now. Now we are only interested in the other 8 roots and their distribution. So we have s to the 8, s to the 7, s to the 6, s to the 5, s to the 4, s to the 3, s squared, s1 and s to the 0. I'm not sure if I'll be able to finish all of it. So 1, 12, 39, 48, 20. The next row has 1, 22, 59, 38. Okay. So I am going to just, I have, because I have already done this, so I am going to cheat on this a bit. I am going to just copy the terms from here. So this is a typical example. So in the next row, if you see here, what we will get is minus 10, minus 20, 10 and 20. You can just compute. This is 1 and 12 minus 22, that is minus 10. So in the next row, here I will encounter this, I think, so let us just cancel out these zeros here. We do not need these zeros here. We can just scale it up down by 10. So now in order to simplify this, in the next row we will get, I believe, minus 20, yeah, minus 22 plus 2, yeah, minus 20, yeah, then probably 60 and a 40. Okay. So again I can scale that differently, so I can get this as minus 1, this is 3 and this is 2. Okay. And then I go to the row for s to the 4, so I will get just 1, okay, this is 2 plus 3, that is 5, and this is 1 plus 2, that is 3, right. Hang on a sec, let me check this. This is 1, 3, 2 is what I have gotten here at the row corresponding to s to the 5. So I think at some stage this is, yeah. Okay, maybe I missed, did I skip a row here? So it is 12 minus 22 is minus 10, so this is fine. What about this row? 20 minus 22 plus 2 is minus 20, minus 59 minus 1 is minus 60, by minus 1 that is plus 60, so this is minus 22, this should be plus 1, no? Yeah, this should be plus 1, sorry about that. Yeah, so this should be plus 1. Yeah, and this should be 1, 3, 2. 1 1s are 2, yeah, so this is 3. So I get a repeat exactly. Sorry about that, I was messing that up. So 1 2s are 2 plus 2, so that's, yeah, I think we will get a 2 here, no? Yeah, we will get a 2 here, exactly. And now in the subsequent row here, you see we will get zeros. It's obvious, no? We will get zeros here. So up until this point, what we have studied is the factor of, so basically then we can say that this s to the 8 plus s to the 7 plus 12 s to the 6 plus so on and so forth till 20 can be written as a factor of s to the 4 plus 3s squared plus 2 times some other q of s. So up until this point I have been studying this q of s. So what do I see in my studies with q of s? In my studies with q of s I see two sign changes. So q of s has two open right half plane roots, and because it is of degree 4, because of course it must add up to a degree of 8, so it has two open left half planes. But from this point onwards I have to take the derivative of this. Derivative of what? This fellow. So that derivative is 4s cubed plus 6s. So instead of doing this I put here 4 and 6. So I can now again reduce this to 2 and 3. So in s squared row now I write 2 3s are 6 minus 3, that is 3 by 2, and 2 2s are 4 minus 0 by 2, that is 2. So yeah, so 3 by 2 and 2. So again I can scale this up and I can write 3 and 4 here. In the next row I can write 3 3s are 9 minus 8, that is 1 by 3, so this is 1/3 and this is 0, right. So now you notice that from here onwards whatever I am studying is again there is no sign change here, but occasionally you might have encountered some sign changes here, no? In case you encounter the number of sign changes, count the number of sign changes. From this part onwards, it is solely dedicated to the study of this polynomial. So no sign changes means this fellow has 4 imaginary roots. So therefore the total distribution is this overall 11th degree polynomial has 3 roots at the origin, 4 imaginary roots, 2 on the open left half plane and 2 on the open right half plane. But if you wanted to study this for the case when this indeed did have some sign change instead, then what you would do is count the number of sign changes. So that many roots of this particular polynomial would be on the right half plane and an equal number would be on the left half plane due to symmetry. Okay. So suppose this was 4th degree and suppose there was, in this case there isn't, but suppose there was one sign change in this part from this row onwards, S4 down. For one sign change it means that there is one root on the RHP, consequently one root on the LHP, so that takes care of 2 roots. So the other 2 roots must then be on the imaginary axis. So in that case the distribution would change and it would become 2 on the imaginary axis, 1 on the LHP, 1 on the RHP, and the overall situation would be 3 on the open RHP, 3 on the open LHP and 2 on the imaginary axis. Okay. So that is the way to study this. So we will see some applications of this Routh array other than this study of this polynomial root distribution, which will then lead us to the next topic, which is going to be study of root locus. Until then, thank you.